Hi, my name is Dan, and this video is one in a short series of videos that I'm going to do on adding using digital electronics. It's part of a larger suite of things that's uh, of videos about logic circuits and digital electronics, which which in turn is part of a larger aim to go from fundamental logic gates through to a fairly simple CPU, and to take you as a watcher, as a student, possibly through quite a long process to go from the principles of logic gates to the principles of CPUs. So in this short series, I'm going to be looking at adding, and the last one is going to be looking at subtracting. So adding is quite an important part of maths, obviously, and if we're going to try and get digital electronics to do maths for us, which is what a computer is at heart, then we're going to need to deal with adding numbers. And computers, as we know, work with binary numbers, so we need to look at adding binary numbers, and we're going to look at the hardware for that over these next few videos. So I've got an example here of two binary numbers, and when you're thinking about adding numbers that have more than one digit, then there are various things to consider. What we're going to do is we're going to look at one bit at a time, and we're going to focus in this video on the least significant bit. So that's the one to the right hand end. If you were in decimal, that would be the units. I guess the same is true for binary. You could call it the units. And what we need is for those two digits is that we need to know what the sum is, fairly obviously, if you're adding things together. And we need to know if we need to carry. So if your hopefully your memory of long addition is that as well as having the sum of the two digits, there's the potential that you might need to carry something into the next column, which is the column to the left. So let's have a quick look at the truth table that this represents. So we've got A and B, which are our two inputs, and we've got two outputs. We've got a sum output and a carry output. As normal with truth tables, we're running through AB as if it was a binary number in its own right. So we've got 0, 0, 0, 1, 1, 0, 1, 1. And for the sum, the result is 1 if either A or B is 1, but not if they are both 1. And for the carry, what we'll do is when we create the digital circuit, we'll have a separate line for the carry, which has got different logic, which is that it's only true if both A and B are true. And looking at those results on the truth table, it's fairly clear that these are simple gates, that the sum is an XOR and that the carry is an AND gate. Okay, so now we're going to go to Digitalworks software, which is simulation software for digital electronics. It's a free piece of software, and a link to where you can get it is in the description below. I should have said earlier on, actually, the roadmap of where I'm going with this larger suite of videos is also down there in the description below. So we're just going to, that's simulating at the moment, so I'm just going to stop it. We're going to create the circuit that does what we've just been talking about. And if you remember a few seconds ago, we want the sum to be an XOR and we want the carry out to be an AND. So let's have two inputs, and we're going to be turning this into a macro. So we use tags rather than interactive inputs. So just have a couple of tags over there, and then we're going to stick in an XOR gate, and we're going to add an AND gate to that as well. And then we'll want a couple more tabs for the output. Here we go. And we're just going to wire these up. So the two inputs go to both inputs for the XOR gate and parallel to the AND gate there. and connect those tags to the output. And we're going to then open the template editor so that we can turn this into a macro. If you don't understand what I'm doing at this point, then you might need to have a look at a video that I've done also on this channel about, well, I've got a small series of videos about using Digitalworks, and in particular the one on creating macros. And so I'm going to name this macro, or this is the name that's going to appear on the box when you add it um, into another circuit. This particular circuit has the slightly curious name of half adder, and you might have noticed that the title of this this video is half adder, and I'm not going to dwell on that. In fact, I'll explain why it's called a half adder, because that becomes more apparent in the next video when we do the full adder. So I'm being enigmatic about that right now. I'm just going to add in the pins that we need for this. So we've got the two inputs, A and B, and we're going to have the outputs, which are the sum and the carry outputs. And we need to go and put some annotations in some labels. So we've got input A, B. Let's just line that up a bit better. And I'm going to use separate annotations for these because these might move about in later things. Add sum. And carry. Now I've labelled that carry out, and that'll become obvious in the next video why I've labelled it carry out. So we need to do the connection process. So we've got A and B inputs. Because A and B should be interchangeable, so it shouldn't matter. Okay. This is the sum output. And this is the carry out. Okay, let's save it. File, save as, and we're in my macros, and we're going to call it adder half in brackets. There we go. So let's create a quick circuit to test that. So new circuit, and we'll be able to drag the adder, and this is where I'm going to actually put interactive inputs and LEDs on the outputs. This should take very long. I feel the need to keep talking whilst I'm doing this because otherwise it seems weird. Me being quiet. So run the simulation, get the thing, the interactive tool. So at the moment we've got 0 and 0 coming in. Our sum is 0 and our carry out is 0. If we make one of A and B 1, then the sum turns to 1. And the carry out is still 0. And let's take the B input separately. That's exactly the same as it should be. And then I should have left that on. Put them both in. Sum goes down to 0, but carry out now is 1. And that is as we expected or as we wanted. So it's quite a simple circuit, this half adder. It's just got the two gates in it. But it's doing something really important fundamentally, which is we're starting to have circuits that do arithmetic and actually do some math for us. And between the adder circuit and memory circuits, which we'll come to in a different series later on in this big suite of things, those two concepts are really, really fundamental concepts when it comes to digital computing. Anyway, that's the simple half adder. The next video I'm going to expand on this into what's called a full adder. Um, but that's it from me for now.